Alrighty, so with quiz coming up, I figure be good to kind of run through this. Make sure you're feeling pretty comfortable with all the 6.1 and 6.2 material. So basically, it's just all about exponential functions, all the things we've learned so far. So it starts off with the graphs and all the key features. When we're talking key features, we're talking about domain, range, intercepts, asymptotes, and behavior. So you can use a graphic calculator, decimals, whatever to kind of age in these if you need to. But for the most part, you should have a pretty good feel of what these graphs are going to look like. So right away when I see this one, I know it's decay because we got a small value here. It's under 1. With every one of these, we haven't really seen any scenario yet where you can find something that has anything but all real numbers as the domain, because we can put anything in for x. Positives, negatives, decimals, 0, anything can be an exponent. The range is really going to depend on if the graph has been shifted at all. So this has no up or down shift. So it's going to have an asymptote here, meaning it's going to approach 0 but never touch it. So we can get everything above 0. This one happens to cross at 1. Remember, technically, whatever the number in front here is going to be the asymptote. So same thing for this problem, it's also going to be at 1. But if you had like a 5 out front here, the asymptote's going to cross at 5. You can see that on the graph. You can see it on the table. A lot of ways to check that out. But it is that a value in your ab to the x base equation. All right, asymptote we already talked about, but it's where this graph approaches but never touches. In this case, it's the x-axis, also known as y equals 0. And again, that's really only going to change if you shift this graph. If you put like a +2 on this and this shifts everything up 2, then it's going to be at y equals 2. So just be aware of, vertical shifts are definitely going to change where the asymptote would be. And then end behavior, just look what happens as x goes to infinity and as it goes to negative infinity. So as x goes to infinity, what does y do? It gets close to 0. And as x goes to negative infinity, what does y do? It goes up to infinity. And so that's all we're talking about for end behavior. There's not really much different over here. Actually, is every answer the exact same? Yep. And sorry, this is the only one that's different because it's flip-flop. Since this is a growth problem, as x goes to negative infinity, this approaches 0. And as x goes to positive infinity, it approaches positive infinity. Other than that, though, it is the same because there are no shifts. It's not shifted up at all to change either of these values or anything at all like that. So a pretty similar problem. All right, next one says to graph it, which again, you can always graph in a calculator. So it says describe the graph in terms of transformations of the parent function 2 to the x. So this very first one, honestly, I don't love because they changed the value here, which makes me think like, well, how'd they do that? The way you actually can do this or figure this out, like to create the same thing, is if you did 2 to the negative x power. And again, we didn't really talk a ton about this, so I'm not super worried about this problem for a quiz or something like that. But if you had 2 to the negative x, what you can do is you can rewrite that as 1 over 2 to the x. Because anytime you have a negative power, that means you're actually just inverting this. So and 1 over 2 to the x is the same thing as a half to the x power. So basically what I'm saying is this is equivalent to 2 to the negative x. And we talked about this in the notes. What's the difference of these? This is going to reflect over the y-axis. So you'll notice there's your base graph. If you graph 0.5 to the x, you get this one, and you get that reflection. So it actually does kind of make sense here, the fact that this is 2 and then this is 1 over 2. Because you're inverting that, it actually inverts the graph across the y-axis, what we call horizontal inversion. Again, not a major one here. This is not one we really talked a ton about. Versus like 4, you should definitely know 4. 4 is the same parent function with a negative out front. Well, then that's going to flip it over the x-axis. So you see this one, just like the parent function, but flipped over the x-axis. For this stuff too, don't forget about what pluses and minuses and stuff do. If you throw like a +7 on the end of this, it's going to shift everything up 7. If you put a -2 here on the x, that's going to shift it right 2. Or if you put +2, it shifts it left 2. So don't forget about the horizontal and vertical shifts as well. Okay. All right. Next one, is it growth or decay? These should be super easy. If your b value is between 0 and 1, it's decay. And if your b value is above 1, it's growth. Super simple. Don't overcomplicate that. Then they ask you what's the y-intercept. And remember, the a value is the y-intercept. So this is going to cross at 0.99. And this one's going to cross at 20. If you ever forget, or you don't believe me or whatever, you can graph these and you can see those exact things. If you type this in your y equals or this one and you jump to that table or you click right on the y-intercept if you're using decimals, it'll just show you that coordinate. So just as a little reminder here, I'll show you this first one once we're loaded up. Come on, little guy. We're getting there. All right, like I said, whether you're using the calculator, whether you're using decimals, it doesn't matter. You're going to be putting in, 0.99 to the 1/3 to the x. And if I go look at the graph, I can see the graph and I can see 0.99 makes sense because it's going to cross here at basically 1. But if I jump to the table, I can see at 0, there's my y-intercept value. So again, you don't need to do this at all because it is always just that a value. So keep that in mind. The only time you may want to look at this is, let's say there is a horizontal shift, or sorry, a vertical shift, like this has like a +7 on the end of it, then this is no longer going to be at 0.99. Like I said, if you put a shift onto here, let's say I throw a +7 onto this, and I go look at it, now it's at 7.99 because it took that was originally here at 0.99, it shifts it up 7 units. So now we're going to see it up here. So again, that's the only time it's not going to be directly the a value, is if you do have any kind of vertical shift there. If it shifts the graph up or down, then it'll also shift the y-intercept, which makes sense, and the asymptote as well. All right, these two are just base population problems where you have a starting amount, you have a growth rate or a decay rate, and a period of time. So remember, if it's growth, you add this to 1. If it's decay, you subtract this from 1. So you'll notice over here, I've got my starting amount of people, 1.013, because it was growth. I added this 0.013. Remember, you convert this to a decimal, add it to 1, and then do it to the power of however many years. Same exact concept here, except it's decay, it's decreasing. So I took 0.014 and I subtracted it from 1 to get this decay rate. After that, I just typed those in a calculator, and that's how I got the new populations. With all this stuff, look at the number, make sure it makes sense. This is a very slight increase, so your number should be a little bit bigger 10 years later. This is a very slight decrease, so it should be just a little bit smaller, even though it's 18 years. It's a long time, but 1.4% dropping is not by very much. All right, so on to the second page, which is pretty short, but a lot of good stuff on here. So first one starts with compound interest. You got Darren, he puts $4,500 in an account, interest rate of 5% every time, but compounded for different amounts. Annually compounded is the equation we've already worked with. It's that AB to the X. So you don't even have to use the compound interest, because if it's just once per year, it's AB to the X. Same thing we just did in the last problem. But if it's compounded any amount of time, your formula, oops, not P equals, sorry, A equals P times 1 plus R over N to the NT. All right. So that's it. Your starting amount, 1 plus, and then rate here is just the rate as a decimal, so 0.05 over the number of periods, which quarterly is 4, monthly is 12, daily is 365. So you'll notice that's the only thing that really changes on all these problems is that N value all the way through. And then from there, what you should expect is slight increases the more times you compound it. Okay, not massive increases. We're barely, not even $100 more when it was compounded daily versus yearly, but it does go up every single time by a small amount. When you're entering these, make sure you do your parentheses right. Make sure you're grouping everything. Really, the key is making sure this exponent is a full quantity. So depending on what kind of calculator you're using, you may need to put it in parentheses. So just make sure that it is that full exponent. All right, what do we got here? We got continuous. As soon as you see that one, that's your PERT formula. So your principal amount, which was 2,000 in this case. E, which is just the E key. If you're using one of the graphing calculators, you got to hit second, and then it's right here, natural log. That'll give you that E. And then to the RT, so rate, 0.04, T, however many years, which in this case was 5. So just if you want to see it typed in the calculator, let's get that 2,000 in there. E to the RT, so 0.04 times 5. So that's what mine should look like. Typed it in, and then I rounded it because it says round to the nearest dollar, so I rounded it up to 24.43. And there we go. Next one here is really just a regression problem, which is the very last thing we learned. And I went ahead and just put this data in my calculator. Now, actually, I did it wrong the first time because I didn't read it correctly. But it says use 0 for 1950, use 1 for 1960. So they're saying you're doing it by decades. So basically, this is 0, 1, 2, 3, 4, 5, 6. And we put those in our calc, and we enter those in. So let me type those in. All right, got those in there. Again, just exactly like I stated, same thing, using 0 through 6 like the problem says. Then we go stat, over to calc, and we pick exponential regression. So this one here, should give us our equation. So our A and our B values, and you notice that's what I've got right here. And I just rounded it. I think it looks like 2 decimal places I picked on those. And so there we go. That's how I got that equation. Now, part 4 was what I actually did the first time, kind of on accident. It says, how could you rewrite this to find the yearly growth rate? So for the yearly growth rate, I simply changed these to 10, 20, 30, 40, 50, and 60. So now this is interpreting every year as a time period versus before it was interpreting every 10 years as a time period. That's the easiest way to do this. There's some other ways you could do this too. You could take this amount and raise it to the 1/10 power, and that should get it for you too. But all I did was swapped out my numbers, and that's how I got my equation. Okay, so that's what I'm saying right there is I did 10 years, 20 years, 30 years, 40 years. So now this calculator is interpreting every year as opposed to every 10 years like we had programmed before. Do my exponential regression. And starting value stayed the same, which makes total sense. But the rate is now much smaller because now it's broken down per year and not per 10 years. So that's the difference on that. Again, nothing too crazy there, but really just making sure you understand how to do the regression model. And then the other piece I talked about was you can get the same rate if you take this, which is the decade rate. Every 10 years it raised by 23%. If you take the decade rate and raise it to the 1/10 power, because you want to break it up into 10 sections, boom, you get this, which is the same rate that we had right here. So multiple ways you can get that. Doesn't really matter whether you want to do the regression like I did, whether you want to do the calculation. Both are efficient. They both do the same thing. Okay, and then the last one says she started with $200,000 in 2015, and let's do inherit it, and the increase to this value. So it says if the rate increase continues, what exponential model can you use to describe the value? So I just figured out what percent increase this was. So I did the 212 divided by the 200 and got that it was 1.06. In other words, a 6% increase. And so at that point, I've got my equation. I know the starting amount, I know the rate to the x. Okay, so every year it's going to go up 6%, and you could use this model to calculate it. So the big idea here is when you divide 2 consecutive years, you can figure out what the rate of change is between those years, or sorry, the percent change between those years. Yeah, so that's pretty much it. If you should be feeling pretty good for this quiz, hopefully, and then yeah, we'll move on from there.